Let's finish out chapter 8, our first of 3 chapters of enzymes, by focusing our discussion about inhibition of enzymes. Okay, we've talked about the mechanism, we've talked about how enzymes act to lower the activation energy, that is, they bind to the transition state best. We had walked through the Michaelis-Menten model and the sequential and ping pong models. So now let's go back to the Lineweaver-Burke plot. Remember that linearized form of the Michaelis-Menten. We will now be exploiting that to identify the particular mechanism of inhibition. And you'll have an upcoming out-of-class assignment that deals with potential murder that I will activate probably in the next few days. So when we think about inhibitors, these can either interact with the enzyme non-covalently, and so we refer to those as reversible inhibitors. Or we can form a covalent complex. Those are irreversible inhibitors or inactivators. Okay, we'll be looking at these in turn. So for our discussion of reversible enzyme inhibition, we'll be coming back, be exploiting this simple cartoon. Okay, so we have our substrate binding to the active site of the enzyme that surrounds it. Okay, that is in the absence of inhibition, the normal mechanism of this enzyme. Okay, well, you will in turn talk about competitive inhibitors. You can see here that the competitive inhibitor binds to the active site. We can have uncompetitive inhibition, where only once a substrate is bound is there a very nearby binding site for the inhibitor. And the non-competitive inhibitor, the binding site for that inhibitor is quite distant from the active site. And so let's look at these in turn. So as we will be looking at the Lineweaver-Burke plots, and you should know what is happening to the Michaelis constant as well as Vmax. Does it stay the same under these conditions? Is one changing or is one decreasing? You should know the trend of these parameters. And so this is a table, perhaps this will help align your thoughts, where we have our Vmax and our Km. The apparent Vmax or Km is what we identify from the Lineweaver-Burke plot, for example. And you can see that some of these parameters will increase, there's a factor in front of it, or they decrease. That factor or modified form of it is in the denominator, thereby lowering that parameter's value. You don't need to worry. These are what alpha and alpha prime are. It doesn't, for your purposes, it does not matter. I want you to know, is there no change? Is a parameter Vmax or Km increasing, or is it decreasing as a result of this, to help you identify the particular inhibitor type? So let's look at these in turn. Okay, first let's turn our attention to the one that is perhaps the immediately easiest to conceptualize. We have the competitive inhibitor. The inhibitor binds to the active site. So if it is bound to the active site, the substrate cannot bind to it. Pretty clear. So we can write out the equation as here's our enzyme. This is a kind of our introduction to biochemistry. You know, we often have curved arrows indicating coming on, binding, and exit arrows, that is departing, okay? Typically a cofactor of some kind, or in this case, an inhibitor. So we have our enzyme substrate coming in to form our Michaelis complex, and of course that can be transformed into the product. If we have our enzyme and the inhibitor comes in, this forms an enzyme inhibitor complex, which we can compete out by swamping it with excess substrate to displace that inhibitor. Okay, so we can either have enzyme substrate complex or enzyme inhibitor complex, but we do not have, in contrast to what we'll see with the other inhibitors mechanism, that we do not have a ternary complex of enzyme, substrate, and inhibitor. We either have this binary EI or binary ES complex, okay? And we can, of course, overcome it by swamping out the system with excess substrate. Now, this is where the Lin-Weaver-Burke plot is quite beautiful. So remember, this is a double reciprocal plot. We're plotting 1 over the initial reaction velocity, 1 over the substrate concentration. Recall from a few slides back that the y-intercept is 1 over Vmax. The x-intercept is minus 1 over Km, okay? And the other characteristic of a double reciprocal plot is as you become closer and closer, approach the origin more closely, the value of that parameter increases, okay? So to discern the potential type of inhibition, you need to have plots that depict in the absence of your inhibitor and in the presence of your inhibitor, and probably even increase, so you can see a trend, increasing concentrations of that inhibitor, okay? So the black plot here is in the absence of inhibitor. So again, this will give us the value, this y-intercept will give us the value of Vmax, and the x-intercept will give us the value of Km as appropriately, as we just described. As we increase the concentration of the competitive inhibitor, what we can see is, as depicted by this red plot, that the y-intercept stays the same, but the Km value is increasing because remember, it's approaching more closely the origin. Okay, this is what I mean by the trend. So because the y-intercept is the same, that tells us that the Vmax is the same. The Km, because this is approaching the origin, this is telling us that the apparent Michaelis constant is increasing. Or if you think mathematically, there's a prefactor in front of it, the value, okay? So by looking at the Lin-Weaver-Burke plot, that will help us analyze and identify with these particular characteristics that this is a competitive inhibitor. Now let's turn our attention to the uncompetitive inhibitor, okay? So here's the substrate can still bind to the active site, and when it binds, very, very close to the active site is a binding site for the inhibitor, okay? So proximity, it's close proximity. That is a key point, okay? Only when the substrate is bound is there a binding site for the inhibitor that is revealed. And we can see that in this reaction description here. So only when you have the Michaelis complex is there a binding site for the inhibitor I. So you have a ternary complex, ESI, enzyme substrate inhibitor, that is bound. That is a hallmark of uncompetitive inhibition, okay? If we swap out the inhibitor's concentration with excess substrate, in contrast to what we saw with competitive inhibition, adding more and more substrate has zero effect, okay? So in the absence, if we look at our Lin-Weaver-Burke plot, in the absence of inhibition, we have this black plot. Here is 1 over Vmax minus 1 over Km as the x intercept. And when we have the presence of a uncompetitive, that's a typo, I never realized that, an uncompetitive inhibitor, it forms a parallel line, okay? And so we can see that Vmax, again, as you get further away from the origin, the value goes down. So we can see that the apparent Vmax decreases and the apparent Km also decreases. And the characteristic shape is that these lines are parallel to one another. Now, let's turn our attention to the non-competitive inhibitor. I do apologize for the similarity in these two, uncompetitive and non-competitive. They are different mechanisms and they are distinct. And I do not understand sometimes why biochemists are not very creative in their naming. So here we are at our non-competitive inhibitor, okay? And so the substrate active site and the binding site for the non-competitive inhibitor is distant from the enzyme, and this tends to lead to a conformational change, okay? That is in contrast to the uncompetitive inhibitor, where the binding site of that inhibitor is revealed only upon binding of the substrate, and it's very close to the active site. Okay, this is a more distant binding site. So if we write out our reaction, okay, we have our enzyme, our inhibitor is present, substrate comes in, forms a Michaelis complex, which can go on to product, obviously. Enzyme and inhibitor for a non-competitive inhibitor will form the EI complex. Substrate can bind, and it can form this ternary complex. So inhibitor can bind to the Michaelis complex to form this ternary complex. So we can have either enzyme inhibitor only complex, or we can have the as a binary complex, or the ternary complex ESI. Okay, that is in contrast to what we saw. The ternary complex is the only species present for competitive inhibition. So for non-competitive inhibition, we have EI or ESI. Okay, the binary or the ternary complexes. So as we saw with uncompetitive inhibition, swamping the system out with excess substrate has zero effect. But what is happening is, because we're pulling away effectively the enzyme concentration, the turnover number decreases. So that is a hallmark of that, this type of inhibition. Lin-Weaver-Burke plot, again, the absence of inhibition is this black curve, 1 over Vmax minus 1 over Km. And what we see is that the apparent Vmax decreases in the presence of this non-competitive inhibitor, but there is no effect on the Km. So they approach the same x-inter slope. So these trends, in interpreting the Lin-Weaver-Burke plot, is very critical for helping you interpret and identify the particular type of inhibition. Okay, and the OOC exercise that's coming up that deals with meta will help solidify these concepts with you. So these are ways that we can describe reversible inhibition. Now let's turn our attention to irreversible inhibitors. That is a covalent, the enzyme is being covalently modified, and these increase in specificity. There are 3 different categories that you should be aware of, okay? This is useful because we're trapping the enzyme and it's covalently modified. This is great for identifying, say, transition states. The complex, when I talked about X-ray crystallography in one of the early videos for this particular lecture chapter, lectures, this traps and starts to give us insight into the mechanism. It's useful for identifying where a potential drug might bind or mapping the active site of an unknown enzyme. You could do mass spectrometry. So you chop up your protein after it's been treated in the presence and absence of this irreversible inhibitor that covalently modifies the protein in a specific location, chop it up with cyanogen bromide, trypsin, chymotrypsin, etc., shoot it into the mass spec, doing sequencing, as we talked about in chapter 3 a few weeks ago, and the peptide in which there's a mass change, most of the peptides are going to be the same. And if there's one binding site that is irreversibly modified by this inhibitor, that one peptide will have a different mass. And so you can do sequencing to identify which is the residue that is modified and what is the binding site. Okay. Do not worry about the specific examples that I'm giving for these 3 groups of irreversible inhibitors. But what you should know is that there is increasing specificity going from more general reagents of irreversible inhibitors to something very much more specific. Okay. So the first category are the group specific reagents. And so these are compounds that react, say, with a certain residue in an active site, all serines in an active site, okay, and covalently modify it. It's not very specific, but it inhibits effectively the enzyme. We can have increasing specificity with an analog that is structurally similar, an inhibitor that is a structurally similar analog to the substrate. So it binds to the active site residues, making those contacts, okay? So it's much more specific for the active site, and this is what we refer to as an affinity label or reactive substrate analog. So we're increasing the specificity as compared to the group specific reagents, like all serines are reacting. With the highest specificity are the suicide inhibitors or the mechanism-based inhibitors. And so this is a substrate that has built in a functional group that will be revealed when the enzyme itself acts on it. That functional group that becomes reactive and attacks and irreversibly modifies the enzyme. This has the highest specificity of all. So the enzyme's own catalysis will generate the chemically reactive intermediate that kills it. Okay. So let's look at these in turn. These are examples. Again, you do not need to know the specifics or the mechanism of these. These are just illustrating the concepts of these 3 different classes of irreversible inhibitors. So with the group specific reagents, you have serines, for example, in this, with the hydroxyl group and interacts with this molecule DIPF to generate the leaving group of a fluoride, covalent modification, death to the enzyme. But this is, it's not specific for which serine, which enzyme necessarily. If that reagent can get into the active site, it's going to kill it. If the positioning is appropriate between the hydroxyl group and the leaving group attack. Okay, the more specific affinity labels or reactive substrate analogs. So these look like the substrate, and they might have a leaving group that leaves as a result of that covalent modification. So as you can see here, this is an analog to the natural substrate of this triose phosphate isomerase. Covalent interaction, the bromine is the leading group. Choo, bye-bye. It is dead. Covalent interaction, no further reactions can ensue. Another example, here's our natural substrate for chymotrypsin. What is this? Phenylalanine. Okay, and so an analog here, phenylalanine, this confers the specificity of this analog to the binding of chymotrypsin, and this is the reactive group that kills the enzyme. So this looks like the substrate. Okay, so this is increasing the specificity. And finally, the suicide inhibitors or mechanism-based inhibitors, only upon acting on this reagent is the reactive group revealed and kills the enzyme. Okay, so the enzyme is converting its inhibitor that into the reactive form that kills it and inactivates it, as you can see in this specific example. This is the greatest specificity because it's very close that the enzyme is actually acting on it in its active site. So weed. And penicillin is a very common suicide inhibitor, as you can see here. Okay. We learned in this chapter that enzymes bind to the transition state best. So, but it is unstable. It's at the tippy top, and it can either collapse back down to enzyme plus substrate, or it can move forward into substrate plus product. Okay. If you make an analog that is analogous to the transition state, okay, it's an analog, it's trapping it at that peak, but because it is an analog, not the transition state itself, which is inherently unstable by definition, we're trapping it in that complex, either reversibly or irreversibly. And there can be no transformation to product or to substrate. Okay, this can provide insight into catalytic mechanism. Antibodies can be formed against, be generated against transition state analogs. Those are called abzymes, to identify new catalysts and so forth. And so an example would be this isomerization between L-proline and D-proline, which we talked about in chapter 2. And so it goes through a planar transition state, and you can see this analog kind of would trap it. Again, these transition state analogs can be reversible or irreversible. And, you know, until a few years ago, probably about 15 or 20 years ago, the bulk of all of our work in biochemistry was looking at the ensemble. Okay, we're looking at the average behavior, the average kinetics, the average binding. Okay, but over the last 15 or 20 years, there have been new techniques that have come online that allow us to dig deeper into the ensemble, to identify subpopulations within that ensemble as a result of probing the single molecule kinetics or dynamics. This has led to great insight in cell biology, biotech, biophysics, biochemistry, okay, and reveals the heterogeneity of that population. So for example, if we have our ensemble average with a particular enzyme activity, we can deconvolute that with our single molecule methods appropriately chosen to look at the distribution of 3 different activities. And this can lead to insight into the mechanism, or perhaps insight into a way of modifying the behavior or something, okay? This has led to a revolution in enzymology, in signal transduction, and so forth. And so some of the techniques that you might encounter, particularly for those of you in lab, in research, or are considering research, would be patch clamp, looking at ion channels. There are several groups on campus that look at that, and particularly in pharmacy and medicine, maybe biology, are doing patch clamping. Single molecule fluorescence. So the sheet cycle group does single molecule fluorescence. Optical tweezers, so this is using light to manipulate molecules. We have that available in my group as well. Anywho, we'll touch on single molecule kinetics and dynamics at various points, but I just really want you to appreciate this is starting to really revolutionize and lead to new insight into our understanding of biochemistry. And just to show you what a single molecule looks like, I have a little video link here. And so in the next chapter, what we're going to talk about are looking at 4 examples that illustrate different principles of enzyme catalysis, the specific mechanisms. And then the third chapter that is focused on enzymes will focus on regulation.